Today we're going to talk about a couple of issues of hypothesis testing, what we would call type 1 and type 2 errors, and their different implications, and a calculation called power, which also leads to a different sample size calculation. Right? There's a homework due Friday that covers these materials in chapter 8. Right? And then, if you're looking at the schedule, exam 2 is actually next Wednesday. So here it is. And, so Friday we'll talk about what's on the exam, and some review sheets, some review problems can be available at that time. So you can look at that over the weekend. And on Monday we'll do some review in class. But the essential material is what we've done on these homework since the last exam. So we've done some confidence intervals and some hypothesis tests. There's some formulas, some matters of interpretation. When would you want to do a bootstrap? When would you want to do, when can you use the kind of standard formulas? And how do we think about this? If you had two procedures and you simulated it under a model, and one, how would you tell if something's better or not? Right? But yeah, so we'll do more of that. The key thing to do is work on the homework. But as you're beginning to review, looking back over the recent things, chapter 7, chapter 8, and I'll have to look carefully and see how much more. Okay, but any questions about this? Okay, so this is your type 1 and type 2 errors. Right? So we're going to start with a hypothesis. You know, theta equals some value, a null hypothesis. Right? And then some alternative that it's not equal to that. Or you could have one-sided if that's appropriate for what you know already. It's an alternative hypothesis. And we gather data. We compute a test statistic. And we compare that to some reference distribution. So our t-tests, the t-distribution is the reference to see whether a t-statistic value is very extreme. Or maybe in Bootstrap, we are bootstrapping the t-distribution and looking at that. For proportions, we can get our z statistic here and compare it to normal. And then we make a decision. And the decision is framed as either we reject the null hypothesis if we have an extreme value of a statistic relative to that reference distribution, or we don't reject it. It doesn't necessarily mean that the null hypothesis is true, but maybe it's reasonable and we don't have strong evidence to say that it's not, right? And in that decision process, we can make a couple errors, right? So a type 1 error is you reject the null hypothesis when it is actually true. This could be called a false positive. And yeah, so that's one type of error. So if you're testing whether one drug's better than the other, and you make a decision that you reject, and you say, actually, oh, this one is actually better, but in truth, there's no difference there. The consequences of that decision is you're going to use that one drug over the other one. And if that other one that you are going to is more expensive, then you're choosing the more expensive drug, and you're not getting any particular benefit there. Right? So in the context of keeping this thing the same, saying they're not the same, if you reject the null hypothesis, you usually have to do something. Or you're making a statement that this area is different from the others. Maybe it has worse health conditions, worse something or other, and then you might decide we need to do something about it. So, but if there's really no difference, you're putting money and resources into something that's not so useful. So it has consequences. Right? to guard against this, we usually set a pretty high standard for rejecting the null, right? To guard against this, type 1 errors, we choose our alpha values to be something kind of small. What is alpha? Well, alpha is the probability we reject the null hypothesis when it's actually true. So alpha is the probability of a type 1 error. It's our significance level. And it's the probability we reject the null hypothesis if H0 is true. Conditional on or given that the reality is that H0 is true. Right? So we choose it to be small so we don't make that type of error too much. Right? So we don't give up on the status quo and force ourselves to do something unless there's sufficient evidence to really prove it. Right? If alpha were 0.25 or 0.5, we'd be changing all the time. And that's not what we really want to do. Right? So we protect that one type of error through a choice usually. Right? The second type of error, though, could be that the null hypothesis really is false, and we do want to reject, but sometimes we don't. Right? Maybe we have a small sample size, maybe we're just unlucky, but we don't reject when it should be, and that has cost too. Right? So the second type 2 error is we don't reject. H0 when H0 is false. So this is a false negative in the sense that a positive result would be rejecting the null hypothesis and cause us to take some action. But in this case, we don't reject the null hypothesis and fail to take any action. So if in fact one drug is better, but we don't get data that proves it, we don't reject and we don't go to the new drug. We just stay with what we have. Or if you're in a manufacturing process and you're testing the output coming along and you're looking for, does it go off the rails and start to produce bad products, and you sample some of them and evaluate them, but that sample doesn't have such a bad average in terms of quality, then you don't reject. But if it actually has gone off the rails and is malfunctioning, you would want to reject. So you fail to take action that could help you. So that's the type of the error. We could give that a probability 2, called beta. The other one's alpha. This is a probability of type 2 error. There's a probability that you, as it says up here, don't reject. Reject. I went down a couple letters there. Don't reject H0 when H0 is false, which could be phrased as some alternative, HA is true. Right? And there's often a lot of ways HA could be true, but some alternative, often that we're thinking about. Right? 1 minus beta is called statistical power. Right? So this is the probability you do reject the null hypothesis and make a decision that leads you to change when H0 is false. So this would be a correct, when you reject the null hypothesis when it's false, that's a correct positive decision in terms of positively making some decision or requiring you to do something. Right? So you want power to be high. Usually if you're planning a study and get to choose sample size and other conditions, you probably want power to be at least 80%. Right? 80, 90%, 90% would be great. If you're doing studies with 50% power, that would mean that there's only a kind of a flip of a coin. Are you actually going to prove it or not? Right? If the alternative is false. That's not a very good bet, right, to do that. So often serious medical studies have a calculation of power where you think about what the alternative is going to be, how big do you think the effect size really is, and then a calculation with sample size, which you really have. And we'll go through a calculation like that.
So you want beta to be small and 1 minus beta, so that 1 minus beta is big?
Yeah. So ideally beta is like alpha, 0.05, 0.10, but often it's taken a little bit asymmetric, where we really don't want the type 1 error to get bigger, so we make alpha 0.05 or 0.01 or something very small. And then power, we see what it is and think about adjusting sample sizes or other conditions. Right? So let's look at some of this stuff with a particular application in mind. So let's say we're testing whether a mean is mu sub 0 versus an alternative, that it's not equal to that. Right? And we have a certain sample size that we're of data, and let's take sigma being known for right now. And so in this case, we can say where we rejected a hypothesis. Right? I will take alpha to be 0.05. Right? So we would kind of choose sample size, choose this. We're going to pretend sigma is known. You can do this when you estimate the standard deviation, but just leaves out one complication to do it that way. And then set up our null hypothesis. So all that's set up, and we're going to reject null hypothesis. Under these conditions, we reject null hypothesis if we get a value of x bar that's far enough from mu sub 0. Right? So under the null hypothesis, the distribution of x bar is going to be centered at mu sub 0. Right? This is going to be our, that arrow is not helpful, right? But the null hypothesis said x bar should be around mu sub 0 and our sampling distribution would be centered here. But if we get an x bar that's too far out, we're going to reject mu sub 0 anyway. So we're going to reject x bar if it's greater than mu sub 0. Now we're under normality. So plus 1.96 times sigma over the square root of n. Or right, if x bar is less than mu sub 0 minus 1.96. Right, sigma over the square root of n. The standard error for x bar is sigma over square root of n. Using normal distribution and 5%, we get these 1.96 numbers, right? So these numbers get related to that. Right? So that's what we reject, right? So what if we have the alternative is true? Right? Well, that's vague as to what it is. So usually you think about some particular alternative, right? So if you're really taking a drug and you think, well, how much better is this one going to be? Is it going to be 5 more units of mercury in terms of blood pressure? Is it going to be 10 more pounds of weight? Is it going to be, a certain amount of extra strength in the manufacturing process? You think about, is it going to be 5 points on a standardized test score? What is that magnitude going to be that's realistic? You can't pretend that your alternative is going to be, solve the world and be the most magical, beautiful thing ever. You kind of have to try to make it realistic to make this work out. So if the alternative is true, right, we're going to choose some value here, some mu sub a value. Right? And I'm going to pretend that mu sub a for our purposes is bigger than mu sub 0. Right? So here's the null hypothesis one. And say, well, what if instead mu sub a is over here, and here's the alternative one? Right? Well, under the alternative hypothesis, the sampling distribution is over here. Right? What we calculated before is if you're out here far enough under the null, see kind of corresponding to the tails of the null curve, this red area is our so-called rejection region. Right? It kind of goes on forever. Right? So if we get any x bar that's out far enough, right, we would reject the null hypothesis and think mu sub 0 doesn't work, right? Is it believable? And now the null hypothesis is true. Okay, so we have a 5% error rate if that's true, because we have 5% tails. Well, what if the alternative is true? What if this alternative is true? What's the probability we do reject? Right? The probability we do reject is going to be the probability we're in the rejection region, but under the null curve. I mean, under the alternative. So under the alternative, there's this area here, right? And that would be the probability we're above this point under that curve. The curve also goes down, and I don't have it quite drawn out right here far enough. There's a little bit of probability under that one, but usually one side is nearly zero, and the other one is most of the power right there. So what's the formula for calculating that area? Right? Well, we want the part of it is probability that x bar is greater than, shift to small. So the next generation of these can be voice activated. So I can say small pen, and it will be right, plus 1.96 sigma over square root of n, given that the mean is actually mu sub a. Right? Another way of saying that is under the alternative. Right, alternative. That x bar is distributed as normal, but with mean mu sub a and standard deviation sigma over square root of n. Right? So we want to calculate the chance that x bar is greater than that when this is its distribution. Right? So any normal, we're going to standardize. Subtract the mean, divide z squared. Yep. So this is going to become a z, and we take the cutoff value, the rejection boundary here, right? Subtract the alternative mean. What is the average under the alternative hypothesis, and divide by the standard deviation to standardize it. Right? So that's a probability that a z is greater than, here's mu sub 0 minus mu sub a, that divided by sigma over the square root of n plus 1.96 is one way to write that. And so as I've drawn it with mu sub a bigger, or we have 1.96 minus something, because mu sub a is bigger, the difference here is negative. So it's going to be something, if this difference is big enough relative to the sigma over square root of n, we're going to get something bigger than 1.96, and we're actually going to be more than half the curve. Right? You want to be in this place. You want to be at least half the curve, if not more. So that'd be one tail area, or one part of the power. The other one was we could be, to fully account for it, we would reject if we're less than 1.96 sigma over square root of n, and we're under the conditions that is this alternative. We would z-score that side too. It's going to be usually trivially small. It's going to be third or fourth decimal place impact because it's on the wrong side of the alternative. So less than, now we would subtract mu sub a, so it's still mu sub 0 minus mu sub a over the sigma square root of n. But now there's a minus 1.96 if we do the same thing. Right? And so that's going to give us some idea of power. Right? So let's do it with some numbers. Right? So let's say that the null hypothesis is that we did the chicken example last time, right? So that the growth weight is 250 grams, and that's our mu sub 0, our null hypothesis. So you're given baby chicks this food supplement, and the previous one got them up to 250 grams, and you evaluated that on a big population, like a whole industry-wide thing. So that's the number that you're doing, and then you're going to give them a new one. So let's substitute this thing, and if it's not equal, maybe it hasn't been tested and to the degree that you're willing to say that it's greater, maybe it's a cheaper alternative. Now you're sourcing your soybeans not from China, but from Brazil or something, right? So you're switching something, and is it the same or is it different? Right? Or a domestic supply, right? You're going to go all Iowa soybeans. Right? So let's say we have 20 chicks, small scale initial study, alpha equals 0.05, and let's say that the standard deviation of the weights is 50 grams. Right? Maybe that's a little big, but whatever. Right? And so when do we reject? When do we reject null hypothesis? Well, X bar has to be far enough away from 250. So qualitatively, X bar far from use of 0 to 50 grams. One thing about hypothesis testing is sometimes it's presented very with symbols and not words, and here's the formula, but the concept is just X bar has to be far away, right? Because then it's not consistent. And so we reject. So if X bar has to be greater than our 250 plus our 1.96, and now sigma, right, I said is 50, and we only have 20 there. And so that number is 272 grams. Or we would reject it if it's too small. If this substitute feed is not as good. And that comes out to 228 grams. So if our observed average of 20 chicks is bigger than that or less than that, we reject. What if our new feed increases the average weight to 275?
And you reject each.
If on average, well, so if we did get a X bar of 275, right, then yes, we would reject, right? But based on a sample of 20, right, even if the average is 275, we might end up with lower, right, just random variability. So what's the probability we reject, right? That becomes the power calculation. So 272, 282, I want to get this. So what if the new feed increases average weight to 275 grams? What, by that, big statement, what is the probability of rejecting the mean of 250 with a sample size of 20 chicks? Right? That's asking what is the power, statistical power to do it. So if it's really 275, we have our two pictures. Like this, the null is at 250, and this one's at 275. Our rejection regions, much like my, is 272 here, or 228, right like that, and below. So we want the probability under the 275 curve that we're bigger or smaller in those rejection regions. Rejection regions are these two things. Right, so the probability that X bar is greater than 272, right, we're going to standardize it. So we're going to make it a z-score, 272. We're going to subtract the 275 because that's the alternative. Divide by, it was 50 over the square root of 20 as the standard error. And so this is the probability that a z is greater than negative 0.268. So it's actually big enough to push this below 0, right? So on a standardized normal, 50% is above 0, so this is the greater than your negative. So you're a little bit bigger. This is 0.606, about 60%. Right? The other one, what's the probability that X bar is less than 228? Well, if you subtract 275 and divide by that, what's the probability that z is less than negative 4.20?
Very small.
That's basically 0 to 4 or 5 decimal places. So the power, right, is about 61%. which wouldn't be great for a kind of study where you want to confirm and prove something. You probably would want to boost it to get a little bit bigger, right? What type of power, how can we change power?
Sample size.
Yeah. Sample size is a big player. And we'll look at that shortly. But any questions on?
Or if we could bring down standard deviation.
Yeah, or you can bring down standard deviation, right? So if you could grow the chickens under more homogeneous conditions, have more control of their sizes and the distribution of feeding so that some don't get less food and some are aggressive and get more food. Or just so if it's more uniform like that, maybe you could cut that standard deviation down to 40. Right? So by control of the process, you might get it better. But let's look at, right, in either of those cases, increased power. Right. So by increasing the sample size, you get better power. By decreasing sigma, you can make the process less error prone, maybe even measurement error, right? Measuring the chicks, if that's done more carefully and you don't add a little bit of extra variability in there, right? There's a couple other things that affect power. If the feed itself is better, right? If you can pull those curves apart, right? If the difference between the alternative and the null, because of your science and your manufacturing and the things that you're doing, make it a bigger difference, it's going to pull those two curves apart. So the chance you're in your rejection region is going to be bigger, right? Bigger difference there. You can make alpha bigger, right? You can make the chance of making type 1 error, you can let that grow to 10%, right? So you don't need to be so far out to reject. But that's usually not a wise thing to do, right? So the basic picture, right, of these things is if you have, curves kind of like this, u sub 0, u sub a, and this is the, it's kind of like, I'm going to draw it the same way by having, if these are the rejection regions, right? The rejection regions don't change, right? Unless you change alpha or n, right? But for that given thing, if this curve moves out here, well, let's try to draw that. So let's say if n gets bigger, let's draw that curve first, because that's kind of the number one way, I suppose. If it gets bigger, what happens, right? Then u sub 0, u sub a, kind of the same. If the n gets bigger, these things get more narrow, right? So then the rejection region can be tighter in around u sub 0. The sampling distribution of this one is also tighter. So if you end up being, okay, here's the rejection region. If this is rejection, this is rejection, with bigger n, because its sampling error is smaller, then the probability out of this other one is practically the whole thing. So you can get a lot of power, if you get adequate sample size. Because then x bar is going to be very, very close to these. If this is truth, it's going to be close to that. If this is truth, it's going to be close to that. And if there's a bigger gap, then it's more separated. Right? That would be kind of the picture for n is bigger or sigma smaller, right? Because a smaller standard deviation by changing the manufacturing and so on would shrink the standard errors and kind of do the same thing. On the other hand, if you can make the alternative mean farther away, so if it's exactly the same picture, same n, so this one is here, and if I can kind of draw this one kind of similar under that, and you're going to get this, our rejection region is kind of the same thing, but you can make the alternative further away, right? So say mu sub a is over here, right? Then this curve should have kind of the same kind of shape over there, but now look at the area, right? You've moved it away, so if the alternative is true, you're going to be shifted farther out. The chance that you're close to mu sub 0 and fail to reject is made even less because the medical or the new scientific advance you have makes more of a difference. And so it's easier to detect. Alpha, you're just playing with moving the rejection region in here, and of course then you get more area under that curve. But we usually don't play with alpha in studies. Right? Let's look at one numerical example, right, to do that. Let's say we do the chicken example again. So the null hypothesis is that it's 250. The alternative is that it's not 250. Right? So now we're going to consider having 80 chicks. How does that change power? Still the same. Sigma is 50 grams. Alpha is still going to be 0.05. So what do we have to do to calculate power in the new reality?
So instead of using the square root of 20, we use the square root of 80.
Yeah. We use the square root of 80, that's sample size, right? We get new rejection points, right? So we can't start right at the end, we have to go back to the beginning and find out where do we reject, right? So we reject, we have x bar is greater than 250 plus the 1.96, and the 50, now it's square root of 80 over here, or x bar is less than 250 minus 1.96, 50 over the square root of 80. Right? So in R, you can use it like a calculator. I started it. I don't really have to close this work, but control L gets rid of that stuff. So, right, 250 minus 1.96 times 50 over the square root of 80. If it's less than 239, remember before we had to go down to 228. Right, to be lower than 228, but with this bigger sample size, we can be at 238 and still reject, because it's based on better information. And then on the plus side, it's that. So what's the probability we're less than 239 when the alternative is a p-norm, the probability for normals? All right, so what we want is 239.0443. If 275 were the mean, we divide by 50 over the square root of 80. And so there's almost no chance of that, right? We're not going to be below 239 if we're really up at 275. So that's nothing. If you do p norm of the other one, 260.9567, right? We actually want 1 minus that, because the p norm does less than that, but on the upper side we're looking at greater than. So we do 1 minus that, and we get 994. Right? That having, but I've typed everything correctly. 50 over the square root. You can also kind of just think about it. 50 over the square root of 80 is a standard error of about 5.5. Right? And so you have to be bigger than, so 250, almost a couple times that 50 over the square root of 80 is you reject if you're bigger than that. That seems reasonable. Okay. And then what's the chance you're greater than 260 when the average is really 275? That's almost 3 standard deviations. So yeah, most of the area is below, or is above that point. This would be a negative 15 over that, so almost -3. So if we could get 80 chicks and do the same experiment, and we really had a difference of 50 versus 7, we would be in really good shape, right? It would be really unlucky to not reject the null hypothesis. You can do these things with the t distribution, right? Just the same. So if you thought, now Q norm of the 975 gives us about that 1.96 value. If we had, let's go back to the 20 chicks we initially had, and it had these two cutoff values. Well, instead of using the normal, if that 50 standard deviation was based on the sample, we would use a t, right? And so we would replace this thing with the quantiles from the t, 0.975, and we used n minus 1 as degrees of freedom. So our cutoff wouldn't be 228, it'd be 226. Right? If we're estimating the standard deviation, we got to go a little farther just to be convinced. And either minus or plus. Right? There. So we have to be above 273. Now what's the probability of that? Well, we have to use the t-distribution again. So we'd use a 226.5993. We would subtract our mean of 275 and divide by the estimated standard deviation of that. And we'd have the 20 minus 1 degrees of freedom. So there's almost no probability of being on the lower side when our alternative is really bigger. But if instead we had, if we beat the upper side, the 273, 273.407, 56% power. Right?
So it's lower.
It's lower with the estimated standard deviation, right? Why is it lower? We're estimating standard deviation, we have to use t. Under the t, it's harder to reject. You need a bigger, more extreme x bar to account for the fact you're estimating the standard deviation and using the t, which is wider. So naturally, you get a little more wider, right? So to be convincing at a 5% level, you got to be out further. And to be out further means there's less chance of actually doing it with 275. So a small change to the numerical calculation if you have a fixed sample size. There's one other thing that can be done. Where am I exactly about that? We can figure out what sample size we need to achieve a certain power. Right? And so now this gets a little bit more involved in terms of the calculation, right? Because we're going to set up a note. What sample size do we need? We did some of these calculations thinking about what type of margin of error we could do. Right? So if you're only looking at margin of error, you have the normal value times sigma over the square root of n. And if that's your margin of error, you can just solve that for margin of error. Right? And that's fine. It's just telling you what your margin of error is going to be for a confidence interval. That also is how big of a difference you can detect. If the x bar is not going to be bigger than that, you're not going to reject it. So it's useful. Right? But in this case, the null hypothesis is the mean is some u sub 0, and the alternative is that it's not that. Right? We're going to and we take alpha 0.05. We have some sigma for a given sample size. We reject h0 if x bar is big, so mu sub 0 plus 1.96 sigma over the square root of n. Or if it's less than mu sub 0 minus 1.96. Let's just do sigma over square root of n. Right? Let's say that then our alternative really is made more specific, and we think we know some idea of what it would be. And let's assume that mu sub a is bigger than mu sub 0. Right? So we really are concerned just with one side, even though we're not specifying that alternative. So let's just keep track of this type. Right, so power, which is 1 minus beta, is the probability that x bar is greater than mu sub 0 plus 1.96 sigma over square root of n, given that the mean is this other alternative, right, like we've drawn it. Right? And so we're going to subtract the mean and divide by the standard deviation and get the probability that Z is greater than, well, mu sub 0 minus mu sub A over the square root of n plus this 1.96 value.
So to solve that for n.
You can solve that for n. So the trick here, right, is that you choose a power. Say power, you want 80%, right?
So you know what the z value
So
is.
1 minus beta is 0.8, and this beta, right, is what, so you know the z value, right? And so you know what your z value is going to be. What z value has 80% above, right? You can look that up, right? So there's a Q norm, right? The quantiles for a certain normal, right? So we want 80% above. Right? So if we look at the 20% point, that is the key, right? So that will, we want a z value greater than, in this calculation, greater than negative 8416. So we want, so this says z must be 0.8416 negative, right? So if we let 8.416 equal this, right, you can solve for n. And that becomes a sample size calculation, right? So here's my power, my probability, except for that little tiny inconsequential thing on the other side. Right? And so we want the z value to be sufficiently big, so we get big, well, small actually, so that we get, we want this number to be sufficiently small so that the normal has a good probability of happening, right? So if we want 80%, we're going to set it at this z value. And so we're going to set negative 0.8416 equal to our mu sub 0 minus mu sub A, sigma over the third of n, plus 1.96, right? Where did that come from? That came from, right, this part here, matching that number. Right? So that's what I wrote. If we subtract 1.96, we're getting at 0.8416 minus 1.96 mu sub 0 minus mu sub A, sigma over the square root of n. This mu sub 0 minus mu sub A, you can pull the square root of n up here. It's kind of double denominator, 1 over, that's it up there. So we're closer to solving than we might think, right? Square both sides. 8416 plus 1.96 squared, right? Mu sub 0 minus mu sub A squared n over sigma squared. And then you can flip those two things onto the other side and get that the power has these two constants in here. Sigma squared over here, and mu sub 0 minus mu sub A, quantity squared. And some people would write these as z values. So this is the z value for
80% power.
like 1 minus beta, and if beta's 20%, that's the point that has 20% above, right? And this is the z of 1 minus alpha over 2 from the two-sided test. And then these things. So the necessary sample size depends on your alpha level, what power you want, what the variability is of the data, and then how much of a difference really there is, right? So if you want more power, this little notation means that as 1 minus beta goes up, you're getting bigger z values. Right? If you want more power, you need more sample size. If you want less type 1 error, right, so if alpha is going down, then this z value is going up. If you want less type 1 error, you need more sample size. Right? If the data are more variable, if the weighted chicks are 60 plus or minus 60 grams rather than 50. You need more sample size. But if you can control the process through uniform feeding, less measurement error, and make it down to 40, you can get by with less. And if you're trying to detect a difference that is actually bigger, right, then you need less sample size. But if these things are close together, right, if these things are close together, then you need pretty big sample sizes, right? So what does it suggest in this chicken example? Well, in this chicken example, right, well, there's 0.8416, right? And then 1.96 was our cutoff value. So we square that, there's 50 squared. And we've said that there's a 250 minus 275 is the difference in the means, right, squared. And it says we would need 31. Right, so 20 was about 60%, 80 was 99%. And so if we want 80%, we should boost it to about 32, right, round it up. A little bit better. So, and so in one application I was in, with at George Washington University, the diabetes prevention program was a study that went on for a few years to show whether lifestyle intervention and use of drugs, metformin, could delay the onset of diabetes. So taking people that were at risk, obese, high elevated blood glucose, but not yet past the clinical marker. And overwhelmingly the answer was yes, that you can have drugs or lifestyle intervention. To do that, well, once they did that, they kept following everybody. Ethically, they had to tell everybody in the study, even if you're on placebo, lifestyle or drugs can help you, and here's the full results. So they could go to their personal physicians and change their treatment plan to help them. So you can't keep people in the dark and make them do bad things once you know ethically that it's right to do. But they kept following them, right? And when I was there the last, the study is expensive, right? 3,000 people, full, extensive medical exams twice a year, right? Cardiology workups and blood workups and everything. So it was $10 million a year to do that, right? Because there's several different research centers and probably 100 people trying to do this. And so the key question to another 5-year extension was power, right? It's what was the anticipated sample size? The benefit, the difference between these groups 15 years after the start of the study, right? Because the first 3 years, there was a huge difference because some people were on placebo, some people were on an active drug, and some people were on lifestyle. Huge difference the first years. But then you tell everybody. And everybody that used to be on placebo is now on drugs or exercise or both. And they're starting to take statins as they get older and all these other drugs, right? So it minimizes the impacts. And so all the weight gain, there's a big difference in weight gain to begin with, and then it kind of came back together. You still see benefits, 10, 15 years down the road of that initial prevention, right? Of kind of I think about it as preserving the body as long as you can, and you whatever benefit you get in terms of muscle tone and other positive impacts of some of these things now carries over later. So the more you do now, it's going to help you later on. But then the question was, if these people have kind of the same weights and BMIs and nearly the same conversion to diabetes and things like that, is there any difference between them that can be still expected? What percent of these people are going to come back? Because if you have dropout, your sample size go down, right? And so if there's not an anticipated benefit of seeing the people over time and spending all this big money on an old study, if there's not the power to do it, then they're not going to fund it. Ultimately, they did for another 5 years, but every 5 years there's going to be this assessment based on what you can project about realistic differences between the three cohorts. Is there going to be any still evidence of any effect? If it's going away, then it's hard to justify continuing an old study when you could take that money and fund new studies. Right? There's also an aging effect, because as weight loss when people get older happens just because they're losing bone mass and muscle tone and other things, and it becomes harder and harder to do the study with older people, right? If they're in nursing homes, they're not going to do the same physical stuff, it's more expensive to get them into air. And so there's many other complications. But a critical question was the power. And it was in a very complex model of change over time. So that's essentially power, right? The 8.5 section of so you have to do one calculation, kind of like this, to find out the power of a study, and maybe a sample size, right? 8.5 talks about interpretation of testing and p-values. Right, so that in many fields there's been criticism over this hypothesis testing framework, setting up hypotheses and calculating test statistics and p-values, because many people think there's limitations to it and how it's done in practice, right? So one limitation in practice is that not everybody reports the studies they're doing, right? So if you have 100 people doing studies and 5 of them get significant results and publish their results, do you believe those 5 are really that special? Right. What is the 5% error rate, type 1 error rate, right? So if there's nothing at all going on and you do 100 tests, 5% of that is 5, and you'd expect to get some things significant just by chance. Well, what if there was 10 out of 100? Well, that's a little bit more, or 15 out of 100. It's a little bit more, but some of those are probably just random error.
How can you tell which ones?
So how can you tell? And if people don't tell you, don't publish all. People don't often try to publish negative data. Right? It doesn't make as much of an impression if you say there's no effect of something or no difference, right? Or our study was inconclusive. I mean, in terms of science, that's often useful. You could have this question. Some researchers at GW as well, on a different, just kind of consulting basis, were interested in orangutans, and are there differences between those ones in Borneo and those ones in Sumatra in terms of their size and the types of trees that are there and these. And there is. One side has big flowering fruit trees and they have smaller jaws because they get to eat nice fruit most of the time. The other ones are eating seeds and bark half the time, and they have big jaws, right? So there's a biological reason, but if you get data from people being out there and test it, you can show that it's. But what if the result has been negative? If you don't publish it, somebody else is going to be out in the field trying to gather these data and spending more money and time. And if you already know something, it's good it's not there. And so there's some value in it, but a lot of journals haven't published that stuff. Sometimes, in clinical trials, and the major medical journals deal with that by having people registering trials. So they say that we're going to do this trial, we're going to test these substances, we're going to have these type of people involved. This is my primary hypothesis. It's going to go this way or that way, and so on. And here's my power. My power is 80% to detect a difference of the size that I think. And so that pre-registration means that even if it's negative, you can search, and even if they don't follow up and try to publish, you can kind of infer that, oh, okay, it didn't really work out so well. There's also this issue of 0.05. Right? Why is it 0.05? Well, back in the early history, as the book recounts, they offered a prominent statistician, Sir Ronald Fisher, what he thought was a good p-value to use, and he said 0.05. Right? 1 out of 20. It seems reasonable, but they're certainly not magical. Right? And there's not really much difference between 0.04 and 0.06. Right? It's the tail area of that distribution. How unusual is it going to be? It's much better to report the p-value itself rather than above or below a cutoff, so you know a little more detail. Report the effect size estimate, report standard errors, communicate as much as you can. Then people can make a better judgment. But often that hasn't been done in the past. So people have only reported some results. Other people have searched through their data for different results. Right? If you have potentially 10 variables that could predict your outcome, and you try them all and then report the best one only, it has a little bit less, scientific, value it doesn't have quite the same weight as if you'd had staked everything on one hypothesis and proved it to work out, right? In the era of genetics and high volume data, a single monitor can give you 1,000 values pretty quickly, and trying to test which of those are related to an outcome and finding the best 5, it's a different thing. In fact, whole new methods have been developed for genetics. There's false discovery rates and whole different areas of statistics that deal with that massive testing problem. Right? And so, so within this, there's another world of multiple testing. Right, where you're testing a whole bunch of different things and kind of searching for the biggest and the best. And instead of doing tests at, say, 5% significance, usually they lower it. If you proved things at 1% significance or even stronger, after you're checking a bunch of things, well, if it still passes that, then maybe it's still believable. So when you're testing a bunch of things and kind of searching, you usually use lower alpha levels for significance to prove something, right? The way I think it's done in practice, in real practice for serious studies, is usually hypotheses are stated up front. And those, your primary hypothesis is usually tested at the 5% significance. Or, if you have a placebo versus metformin, placebo versus lifestyle, you might test each of those at 0.025, just split it in half. Right? And if both of those pass, at that more stringent level, that's still convincing. But then there could be secondary hypotheses. And maybe you have, 6 or 8 secondary hypotheses that seem pretty reasonable, but they're not the primary purpose, right? Are there differences between males and females on those different drugs, right? Is there an age interaction, something like that? You might take the 0.05 level for those and say divide it by 10. Maybe they have to pass at 0.01 or 0.005, so you got to get more significant results for that. Right? And so it's clearly divided, main hypotheses, secondary ones. And then you get a section where you do exploratory work. You don't claim that you've proven those things necessarily, but it's kind of interesting to see. It could lead other people to do more work later, but you're kind of clear in your communication, listing what's primary, what's secondary, what are you going to explore beforehand, and then following up and kind of presenting that way. So it's kind of more honest, but it's kind of hard to get that across all fields. Medicine's very advanced because it has to be, right? Because of the stakes and the $100 million to develop new drugs. So, they're not going to mess around with that. I don't think, or the medical journals won't let them. And so, what are you confirming a past result versus what are you exploring needs to be there. And so there's some things with interpretation that make it a little bit dicey. Some people some journals have gone and said, we don't want p-values, we don't want testing anymore. We only want description, we want confidence intervals. Confidence intervals kind of are the flip side of hypothesis testing, so I don't know if that really solves it. And I think there's nothing else besides communication, right? Dealing with what assumptions are underlying tests, what have you done exactly, what are limitations. I've had a couple papers published that I felt the reason they were published is because I wrote the limitations well. And they said, okay, well, he admits all that, so we still publish it anyway. So, okay. But so there's some interpretation that's kind of interesting to see in there. The numerical thing we can do is calculate power, calculate sample size necessary, and we'll primarily do this. If you look online, there are sample size and power calculations for whole ranges of different things. So, depending on different more advanced models, there's different ways of calculating. But at the core, it's the same idea. Like we figure out where do we reject for what type of test statistics when we compare it to some reference distribution, and then what's the chance that we do it, given a certain alternative. And so that same framework is used in very complex models to make decisions about study planning and then evaluating quality of studies. So, but any questions about those? So the homework goes through some of the hypothesis testing in the chapter, and then some of these issues with interpretation. Yeah, thank you.
Do the abstract.
Yeah.
I really didn't like that second one.
Just to let you know, I won't be in class on Friday.
Okay.
Going on the LEAP retreat and
Oh,
like
okay.
one of the leaders of it. So
Oh, good.
to leave at 1:30 to get up to the shrine.
Have
And
you done things up there before?
yeah, this is like my fourth one I've been on, so I feel good about like leaving it.
Yeah.
But that's also why I haven't been really going to the morning class because it's just been like
did
a,
so much,
a hard
yeah.
week. Yeah.
Well, that's the
Busy.
nature of auditing. It gives you
Yeah.
flexibility that way.
That's the
so,
thing.
Yeah.
Yeah. All right. Yeah. Just want to let you know I won't be here Friday.
Okay,
but
we'll have a good time up there.
Yeah,
Hopefully,
thank you.
Hopefully you have good weather.
Yeah, I hope so. It should be good.
My
I'm
daughter
not sure,
had
but it'll be good.
cross country in middle school, and then so the state championships for cross country were last weekend on Sunday during the rain. It
Oh,
was so miserable.
that's awful.
Because it was
like running in the
cold.
mud.
Yeah, it was in a
Rain.
field with,
Not
just
good.
like, it was puddles this deep, and kids
Just running right through
going
it.
around the curves, and people fell down.
Oh
It was
my
like,
gosh.
it was, we didn't stay for the award ceremony because it's so,
It's too much.
soaked through, so.
Yeah.
Anyway, we'll have a good
Yeah,
time
that's
up
awful.
there, so,
Thank you so much.
no,
All right, have a good one.
you too.